chemical bonding, what is the purpose of chemical bonding? Why does chemical bonding, why do atoms form molecules at all?
To achieve stability.
Correct. Okay, so like the whole aim of every single atom everywhere is to achieve stability. Stable state means lower in energy. Okay, this is like a base rule you'll find in all of chemistry. So if you have like two different processes that can take place, the one that naturally is preferred is the one that goes towards stability. So remember this rule even when we're doing organic chemistry, even when we're doing like, I don't know, redox or thermodynamics or anything, stability is the way. Okay. So what is the way that atoms can gain stability? What are they looking for when you say stability?
Either gain or lose electrons to achieve like a complete shell or like symmetrically perfect shell.
Close. Gain, lose electrons, again, that's one of the many ways that atoms get stability.
They want to like complete the number of electrons in their last shell to an octet or the duplet.
Correct. The main thing is to attain octet. Hi Rishit, good afternoon.
Hello, ma'am.
Yeah, it just started, so don't worry, you didn't miss a lot. Okay, so octet is the main aim of any atom. That's like the tier 1, like the S class of, getting stability. If that is, that's really difficult, like in the case of D block or F block elements, then they'll settle for other stable enough configurations, like good enough. So that can be half-filled configuration, or just ensure that whatever orbitals they have, are they all completely filled or not. That's like the next best thing that atoms can settle for. So whatever phenomenon happens naturally in nature, you can find that the driving force between that is, one of these two. They will aim for octet, 8 electrons in the outermost shell. Otherwise, the next best thing is just pair up all the electrons, get half filled or a completely filled configuration of whatever orbitals there are. Okay. So the first theory, remember, again, we are following the same route as what happened in atomic structure. Like chemical bonding theories were not figured out after we figured out the structure of the atom. Both were happening like simultaneously. Okay, so the first theory is like extremely simple. No one knew about atomic orbitals, like orbits or what the structure of the atom is at all. No one knew about SPDF and all of that. So the simplest theory is people like Lewis. So Lewis and Kossel, they teamed up and then they postulated, they were the first ones to talk about the octet rule. Okay, so they were the ones who said that atoms form bonds in order to achieve octet configuration in the outermost shell. Now, what are the different ways that atoms can achieve the octet? So this ties in
Either give or donate or share.
Correct. So different ways that atoms can get octet is one, they can directly lose or gain the required number of electrons. In which case, what do they form? If an atom loses or gains electrons, yes, forms ions. In which case, what kind of a bond do ions have between them?
Ionic bond.
An ionic bond.
Ionic bond, also called electrovalent bond. Electrovalent or ionic bond. So the driving force between this is the attraction between opposite charges, positive and negative, attract each other, and that's how the bond is formed. Okay. Acha, before we get into it, this whole chapter is about chemical bonding, right? So chemical bonding is what type of a force? Is it an attractive force or a repulsive force?
Attractive force.
Attractive force, correct. So wherever you see that there is a chemical bond forming, the driving force behind it is always attractive. Because that's how, like, things need to get together in order for a bond to form. Cool. What is another way that atoms can achieve octet? Sharing of electrons, correct. So they can either lose or gain the required number of electrons, or they can share their electrons with other atoms, in which case there are two types of bonds that fall in this category. One is your covalent bond, which you're pretty familiar with. And another kind of bond that comes under this category where electrons are shared is called the coordinate bond. Okay. Do you guys have any idea about coordinate bond? Have you heard of this term before? And in what context did you hear of it? So electrovalent bond you're familiar with, ions hote hain. Covalent bond also you're familiar with. You have seen example cases also. So have you heard of coordinate bond? Yes, no, no one?
Like I've heard
No,
it
ma'am.
in our class, like they share electrons, same case over here.
Acha, you heard only this much. Okay. So coordinate bond is a special case of, okay, it's not the same as covalent bond. Yeah, it is a special case of chemical bonding where electrons are shared. Just that electrons are not mutually shared. So covalent mein kya ho raha hai? If you take Cl2 ka example, covalent bond is like both the Cl, so this Cl is giving its electron, this Cl is giving its electron, and the pair of electrons is shared between them, right? So this is like a mutual sharing of electrons. Both the atoms are giving one electron each, or two electrons each, or three electrons each. In coordinate bond, only one atom gives both pairs of electrons to the other atom. So it's not mutual. Only one atom is giving a pair of electrons to the other atom, and that pair is being shared between both the atoms. Okay, so that is coordinate.
What is that atom gaining?
So this happens when one atom has like excess electrons, as in not more than required. One atom, you say it is electron rich. Okay, like for example, in the case of water molecule, you have HOH, right? So this has like two lone pairs of electrons. So there is a high density of electrons on the oxygen atom. Similarly, in the case of nitrogen, ammonia, not nitrogen, ammonia is NH3 plus nitrogen has a lone pair of electrons. So on one side of nitrogen, there is excess negative charge, like, it's an electron rich area. So cases like these, you have electron rich species, and then you have some electron deficient species. Like if you take D block elements, so coordinate bond is mostly like 90% of the times you find it with D block elements. So for example, if you have iron, whether iron forms a +2 or a +3, it loses the s electrons and it has empty d shells, right? Like a lot of unpaired electrons are there in the d shells. So these kind of cases, iron has space for extra electrons. There are like ions and molecules that have, extra electrons. So the lack of electrons attracts this presence of, electron rich ammonia, and then there's like a coordinate bond formed between both of them. So ammonia gives both of their electrons to the iron atom, and they're shared between the nitrogen as well as iron. So that's kind of the scenario where coordinate bond is formed. So covalent bond is mutually shared. Coordinate bond mein one electron rich atom is sharing both its electrons with the electron deficient atom.
If it's electron rich, then why don't they just form an ionic bond?
So that is the reason, right? Like ionic bond ke liye, ions are defined as something that has like it has proper positive charge and a proper negative charge. It needs to have gained or lost electrons for it to be an ionic bond. This is something between an ionic and a covalent bond. Yes, it is formed just like ions where something that has a partial positive charge, something that has a partial negative charge, they are coming together. But this is not electrostatic forces of attraction. Species are not separate. These electrons are actively being shared between them. Ionic bond mein electrons are not shared. It is purely, oh yeah, you have an opposite charge, so I'm attracted to you. In the case of coordinate bond, there is an active sharing of electrons, like these electrons are placed in the orbitals of the d block. They are there outside this thing and they are shared between both the atoms.
Can you give another example of coordinate bond? I'm still confused.
I mean, like it's a whole thing. Like just to give you a brief, instead of just saying the name, I wanted to give a little bit more information. So you can think of it as coordinate bond being between ionic and covalent bond. Okay. So there's special class of compounds called coordinate compounds, and we will get into the whole thing of how they are formed, what is their structure like, and how do they, okay, reactions are not there, but like why the color, the magnetic properties, like all of that, we'll get into it in grade 12. There's a whole chapter on coordinate compounds itself, so don't worry about it. But essentially, coordinate bonds is something between ionic and covalent, where they're like ionic, you have like electron deficient and electron rich species coming together, but like covalent, there is sharing of electrons. The difference between coordinate and covalent is that covalent may there is mutual sharing, coordinate may one species is donating excess electrons to the other species. So Kaveri, you asked for more examples, right? In this chapter itself, we'll come across many cases where you find a coordinate bond. Like carbon monoxide may there is coordinate bond. Carbonate ion, I think, has a coordinate bond. Like nitro group has a coordinate compound, like HNO3 and all, nitrate ion and all. So you will come across this. This is just, I'm just giving you the terms so that when we come across it later, you know what to call it. Okay. Coordinate bonds you will find in other places, but majorly in D block. Yeah, Sana?
Excuse me, ma'am. Do we have coordinate bond like in our syllabus?
No. I told you, right? Like all about coordinate compounds, you have a whole chapter on it in grade 12. So in this chapter, we will be going deeper into it. All right, so these are like the different types of bonds formed by atoms. Okay. The driving force behind what kind of bond an atom forms, what is the driving force? Like what decides what kind of bond an atom will form?
Valence electrons.
Correct. Or in other words, you can also call its valency. Okay. So, for example, if I take sodium, what is the valency of sodium? So
+1.
+1, yeah. So valency essentially comes from the number of valence electrons it has. So yeah, that is absolutely right. So sodium electronic configuration is 281. Because it has only one electron, its valency is +1. Meaning it is going to lose one electron in order to form an Na+ ion. So as such, because of this, what will you expect sodium to form? What kind of
Cation.
yeah, Sodium forms a cation. What kind of compound or chemical bond does sodium take part in majorly?
Ionic.
Ionic bond.
Correct. Okay, so that is the connect. So once you figure out the number of valence electrons, usse you will get the valency, and from valency you can figure out whether it will have a tendency to lose gain electrons or share electrons. Okay, but the main aim for all atoms, like whatever it does, the valency comes from the fact that it needs to have octet configuration. Octet configuration. Okay. Okay. So you have Lewis configuration. Do you know how to do, like, do you know what are Lewis symbols and how to figure out the Lewis notation for different atoms, for different molecules? Are you familiar with it?
Not sure. I guess it was done in the class, but I don't remember it.
Acha. So Lewis notation is like this. You are very, very familiar with. Maybe you just don't know it's called Lewis notation.
Is it a dot structure?
Correct. Yes. So this is the notation where you use dots or crosses to represent electrons. And the way you represent electrons is on, around the symbol of the element. Okay, so if you were to represent individual atoms, for example, again, if I take sodium itself, another main point is you don't represent all of the electrons. You only represent the valence electrons. You ignore the inner electrons, which are not taking part in bonding at all. So coming back to sodium, iska electronic configuration is 281. So valence electron is just 1. So in Lewis notation, you will show sodium like this, Na and 1 single dot. And if you take oxygen, for example, oxygen is 2, 6. The 6 electrons you will distribute around the symbol of this element. Symbol is O, and 6 electrons you can use either dots like this, or you can write it as a cross. So 1, 2, 3, 4, 5, 6. Okay, so this is what is Lewis notation, also called Lewis's dot structure, where you use dots or crosses. Okay. So now is it familiar?
Ma'am.
Yeah.
I have a doubt. So like if we have like neon, then will it be like 8 dots or like 0 dots?
8 dots. Valence shell mein jo bhi hai, you consider that. So neon is completely filled. So 1, 2, 3, 4, 5, 6, 7, 8. So it is completely filled. You can see that you can't put dots anywhere else. All 4 sides, all 8 electrons are filled. So neon ka valency is 0. No reaction. So when you write compounds in Lewis notation, that's exactly what you're looking for. Can you write it in a way that there are 8 electrons around each symbol of the atom? So if you're talking about compounds, Lewis representation of compounds, let's go with oxygen itself. So oxygen, to complete octet, how many more electrons does it need?
2.
2 electrons, correct. So what sort of a bond can it form? If I
A
have
coordinate bond.
Between 2 oxygen, what sort of a bond will you find?
Covalent.
And how many electrons will be shared between both the oxygens for covalent bond?
Double bond.
4.
Oh wait, 4.
let me put it this way. How many pairs of electrons will be shared between the two oxygen atoms?
2.
Two.
Everyone agrees it's 2 pairs? Pakka?
Yes, ma'am.
Yes, ma'am.
You're right. Needs 2 electrons, so it also needs to give 2 electrons. So covalent bond mein it's a mutual sharing. So which is why it's gonna share 2 pairs of electrons. So 2 electrons shared by this oxygen, 2 electrons shared by this oxygen. Remaining 4 electrons will be distributed around it. 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6. So this is like the Lewis representation for compounds also. So see that all of them have 8 electrons on each side and you're set. That's satisfied. Okay. Covalent bond represented by Lewis dot structure. This is how they are represented. So again, this also you must be aware of. Multiple pairs of electrons shared. So if there's one pair of electrons shared, what kind of bond is formed there? What kind of covalent bond is formed?
Single
One
bond.
pair of electrons. So if there's one pair of electrons, that's a single bond. And single bond is represented by a single dash. If there's 2 pairs of electrons,
Double bond.
double bond, and that's represented by
2 lines.
2
One
dashes.
on top of the other.
And if there's 3 pairs of electrons, that's a triple bond.
Triple bond.
That's 3 lines. Okay. So this is how it is. You guys have subjective paper also, right? So we will practice writing Lewis dot structures for a few things. Okay. All right. So how do you write Lewis dot structure? Is like, this is the first step in figuring out the structure of a molecule. Okay, this will help you with VSEPR and all of that. And this was like the first ever theory proposed with respect to chemical bonding. Okay. So how to write Lewis dot structure is, so there's a whole methodology given in your textbook. So step 1 is get the total number of electrons. So let's do this, for example, for carbon dioxide or carbon monoxide. Let's do it for carbon monoxide actually. Carbon dioxide to pata hai. Carbon monoxide is CO, right? Can you guys figure out the structure for carbon monoxide? How is the sharing of electrons taking place here?
Double bond with
Double bond, so C double bond O. So C has 4 electrons, 2 of which it is sharing with oxygen, but that does not complete octet of carbon. No, total it will have double bond, say 4 electrons plus these two 6 CRF. So how is getting carbon, like how is carbon getting electron number 7 and 8? So there's like specific steps towards figuring it out. So we'll do that with carbon monoxide. Okay. So carbon monoxide may get the total number of electrons. How many electrons does carbon monoxide have?
Just the valence shell or all in all total?
Valence. This whole chapter, right? Whenever I reference electrons, you can assume that it's valence electrons, because inner electrons are not going to bother with chemical bonding. If they're coming into picture, it will be specified. Okay. So here you can default assume it's going to be valence electrons.
10 electrons.
Total is, so carbon has 4 valence electrons, oxygen has 6 valence electrons, so total is 10. Okay. Next, step 2 is if you know that something has a tendency to form anions, like for anions, add, acha. So this is if the species itself is, if it is a cation or anion. So this is what it will help you figure out. So if in case the species you're figuring out the structure for is an anion, you add the number of electrons equal to the charge on the anion. And if the species happens to be a cation, like ammonium ion, NH4+, then you subtract the electrons equal to the charge. Okay. So anions in the sense, like suppose you're trying to figure this out for carbonate ion, CO3 2-, or SO4 2-. If you're trying to figure out the structure of these species, these are not neutral molecules, right? So jitna bhi charge hai, those many extra electrons are present in the whole structure. So you add those many electrons, and if in case it's a cation, like for example NH4+, then you subtract the electrons equal to the charge, because this whole species is lacking those many electrons, isliye the plus charge happened to be there. Okay. Now, will you do this, like is this step applicable for carbon monoxide?
No, because it doesn't have any charge.
Yeah, carbon monoxide is neutral, so you can ignore this step. Now, step number 3 is, again, you estimate, like basically you guess the distribution of electrons based on the symbols and the skeletal structure. Like, for example, so one, if you had to figure out the skeletal structure, if you had a polyatomic system like carbonate, sulfate, or ammonia, one of them is the central atom, and then everything else is distributed around it, right? So and then once you have the basic skeletal structure, then you need to distribute the electrons. Like, you know that oxygen by default has 6 electrons, which means that when you are figuring out the structure of carbon monoxide in this case, oxygen cannot have 4 electrons, because by default it has 6 electrons. Maximum, you can have more number of electrons because it is sharing with carbon, so carbon might have contributed it, but you can obviously, like, you cannot put like just 2 electrons on oxygen. So based on your knowledge of the elements and how the skeletal structure is being formed, you can guess the rough distribution of electrons. Okay, so yeah, so based on that knowledge, how many electrons would be around carbon and how many around oxygen? What would be your first guess of this? Take it one step at a time. How many electrons should be around carbon?
8.
Ideally 8, yes, but we have a total of 10 electrons, right? So if you distribute 8 electrons around carbon, oxygen is not gonna have any. So how should the distribution be between both of these?
Will it be 4 itself?
Huh?
Will it be 4 only for carbon?
You can start with 4, yes. But obviously, since there is a bond formed between these two, there's going to be extra electrons somewhere in the mix. So like, dictate the placement of electrons to me. Like, so if you think carbon should have 4, how should I distribute it? Like 4 of them independently, How, like, what sort of a bond do you
Of
think?
them like between carbon and oxygen out of the 4.
How many between carbon and oxygen?
Like 2 from carbon side.
2 from carbon side. Okay. And remaining 2. So if carbon is giving 2 electrons, it means that oxygen is also sharing 2 electrons. So double bond ban gaya. So 1 to 4, 10 में से 4 electrons we have distributed it. So we have remaining 6 electrons. How do you think that is it arranged? Are they all lone pairs?
I have a doubt, or rather, I think I may have the answer to this. I'm not sure. Is it possible that like they have a double bond and then like a coordinate bond where oxygen gives like 2 electrons to carbon and completes like its octet?
Awesome. So that's exactly is the structure of carbon monoxide. Okay. So yeah. So how did you figure it out, Ritu? Like, how did you get that idea?
I think my teacher said it. I wasn't entirely paying attention.
Okay, you were paying attention in your class, basically. Okay, so carbon, 4 electrons. Out of that, let's say you guess that 2 electrons are being shared. Remaining 2 electrons, if we put it here, there's 6. 10 में से 6 electrons we have given positions for. And then we have another 4 more electrons. If we put them around oxygen. So this way, oxygen ka octet is being completed. It has 2 lone pairs plus 2 bond pairs. So total 4 pairs, matlab 8 electrons aa gaye. Now carbon ke octet is not complete. But if these two are forming a molecule, it means that carbon ke octet also should be somehow completed. So then you can figure out that, okay, oxygen may there's excess, like this is an electron rich species, it has extra lone pair of electrons. So oxygen is going to share 1 pair of electrons to carbon in a coordinate covalent bond. So technically the structure of carbon monoxide, you will have C triple bond O, out of which only 2 bonds are like proper covalent bonds, and the third bond is a coordinate covalent bond from oxygen to carbon. Okay, so let's do another example. Before that, so skeletal structure के लिए central atom, center में जो भी है, is usually the most electropositive atom. So जिसका भी electronegativity सबसे कम है, that sits in the center. And another thing is, once all octet is fulfilled, distribute the number of electrons as the lone pair of electrons around the center. Here. Okay, based on this, can you figure out the structure of sulfate ion? SO4 2-. Let's not put dots. Okay, sulfate ion में which atom is the central atom?
Sulfur.
Sulfur.
Sulfur is the central atom. क्योंकि sulfur oxygen में से oxygen is more electronegative, sulfur is less electronegative, so that's going to be in the center. So oxygen distributed around it, there are 4 of them. So let's just put all 4 of them equally on each side. Okay. Now, this whole thing has 2-, so 2 extra electrons hai. So what is the total number of electrons that sulfate has? कितने electrons है total sulfate ion में?
30.
30. So sulfur also has 6, oxygen also has 6, so 6 5s are
36? No, wait, 34.
Calculate कर लो ना. 34 कैसे?
32.
Guys are 30.
So
I'm 32.
6 5s are 30.
And then the charge would be
And the charge will be
added, so it will be 30.
added. So 32 ions.
Correct. So 32 electrons are there in this ion. So you need to distribute these 32 electrons between these 4 atoms. Okay. Now, how should we do this? So sulfur has 6 electrons. So let's just start with, a single bond between all 4 atoms. Okay. Itna to minimum hoga to form this particular ion. So 32 में से 8 electrons have already been distributed. Now what about the remaining 2? Remaining, whatever, 32 minus 8, 24.
It could form a double bond with 2 of the oxygens.
Okay, double bond. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So remaining 22. So that's like sulfur has 1, 2, 3, 4, 5, 6 already, like 12 bonds there. Like sulfur would not be able to take more than this.
How many electrons are done?
10 electrons done. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Sorry, 12 electrons done. So 12 done matlab, so there's remaining 20 electrons. So double bond, these would go as lone pairs to oxygen. So both these oxygen ke octet to complete ho gaya. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8.
And sulfur also octet is complete, right? With those 2 double bonds.
Yeah. We can't put any more on sulfur. Yes.
So then we could just add like coordinate bonds with the other 2 oxygens.
No, इनके भी lone pairs रहेंगे ना. So you have 1 electron of this oxygen, 1 electron of this oxygen. मतलब remaining 5 to should be around here. Oxygen by default has 6, no? Out of which 1 it is sharing here. So और कितने बचे? So there's 1.
Won't there be one more in the oxygen?
No, that's what I'm checking, like how many more. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Plus 8 is 28. So 4 more are there, right? So they will be distributed as lone pairs on oxygen. So in दोनों के octets भी complete हो गए. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So this is the structure of sulfate ion. So this is the
I didn't get one part, but then won't sulfur have like 10 electrons, like more than 8?
That's more than 8, right? So you have sulfur has like total of 12 electrons. 1, 2, 3, 4, 5, 6 bonds, matlab 6 into 2, 12 ho gaya. So this kind of a case is something called an expanded octet. Okay, so these kind of cases are found in multiple scenarios, like not just sulfur, even phosphorus, even chlorine, like a lot of P block elements. So you'll find this mainly with P block elements. They are capable of forming something called an expanded octet. So this was one of the main reasons why Cossel-Lewis structure or their theory has failed. Like Lewis's whole thing was bent on the fact that atoms want to gain octet. But there was another thing that we had talked about, remember? Like if not octet, then atoms are also happy forming something more stable. They are also happy with a completely filled orbital or a half filled orbital, like any other stable configuration as well. And this is like a sulfate ion is one of such examples where sulfur doesn't have an octet, yet sulfate ion is stable and happily existing in sulfuric acid and in your different sulfates and everything else. Okay, so this is like a strike against Kossel-Lewis's theory. They were not able to explain how, explain the case of expanded octets. Like, how is this possible and how is this occurring? Because at their time, they didn't have the knowledge of atomic orbitals or, what is happening in the atom. They were just trying to explain okay, we know that this has so many electrons. These are the kind of bonds it forms. Like it has, so this is the valency of oxygen. This is the valency of sulfur. Based on that, we also know that gases like neon and argon did not react. So based on this, how can you explain chemical bond? An assumption of Lewis was that he imagined atoms to be like you have the kernel nucleus along with the inner atoms, so that he called something as kernel, like a coconut kernel sort of a thing. Okay, so kernel consisted of your nucleus and the inner electrons, and the outer electrons formed like a box around it, like a cubical structure around it. So 1, 2, 3, 4, 5, 6, 7, 8. And in order to form this box, you needed to have like all 8 corners of the box filled with electrons. And that's where he came across, that's where he proposed the idea of octet. Like that's how he came up, that's how he visualized why is 8 the magic number. Because he imagined that the outer electrons would have formed a box and they needed 8 electrons to complete all the corners of the box. So that's where the idea of octet configuration, that's how he visualized it. Okay. But yeah, so clearly in the case of expanded octets, as well as you have cases like electron deficient species also. So electron deficient species, the example is something like BCl2, BF3. This is a very good case, BF3 in fact. So boron trifluoride, BF3 or BCl3 is known to have covalent bonds. But if you try to explain it with covalent bonds, boron is just forming 3 single bonds with the 3 fluorine atoms. So in that case also, the octet is not getting fulfilled, yet this compound exists. So expanded octet and electron like deficient species, Lewis' theory was unable to explain. But it was a good starting point because he gave the whole Lewis notation aspect of it. You can easily denote single bond, double bond, and triple bond. Okay, so that is what you take away from Lewis's whole proposal. Okay, then you have the concept of formal charge. So speaking of formal charge, are you guys aware of oxidation states? Have you heard of the term oxidation states, Pele?
Yes, ma'am. I'm not sure what it is, but I've heard of it.
It was in the periodic chapter.
Acha.
It's like valency, but with charge.
Excellent. Yes.
And it depends on the more electronegative element in the compound.
Yeah. So formal charge, you can think of it as, the precursor to your oxidation states. Again, you can look at the name and figure it out. So it's the charge that you think would be expected to present on an atom. Like it is just for formality sake, just for our own understanding. It is not like a true charge. So you can apply it to covalent compounds also. It's just, it's basically like oxidation state. You can understand it as oxidation state. Okay. So how do you calculate formal charge? Is the formal charge on an atom is equal to the total number of electrons, or you can say the total number of valence electrons in the free atom, like in the natural state, minus the total number of lone pair of electrons minus half of the total number of bond pair of electrons. Okay, or you can also call it shared pair of electrons. So the way you can understand it is, if an atom is forming a chemical bond with another atom, how much charge has it technically, like how many electrons has it technically gained or lost? Okay. So for example, if you consider, like we had figured out the structure of carbon monoxide, right? So structure of carbon monoxide is you have C triple bond O. Carbon has one lone pair of electrons, and oxygen, like apart from this, you would have one lone pair of electrons. The other two are shared between both of these. So what is the formal charge on carbon? So to figure it out, what are the total number of valence electrons in carbon, like by default? Calculate this, no, you guys? What's going on? You there?
Yes, ma'am.
So formal charge on carbon क्या होगा?
I'm just not sure about one thing. In the shared pair of electrons, we won't count the axial bond, I mean the coordinate bonds, right?
No, all of it. Because it is still a shared pair, right? All of the shared pairs. Take it step by step. So formal charge on carbon, what is the total number of valence electrons in the free atom? How many valence electrons does
4.
carbon atoms have? 4 minus,
Charge on carbon is 0.
huh?
Is it like no charge? Because if total number is 4 minus lone pair 1, that's 3, and half of 6, that's also 3. So is it 0?
Okay, total number of lone pair of electrons. So there are two electrons, right? Lone pairs mein.
Yeah, so one lone pair, right?
One lone pair, you're considering the number of electrons. So either be you've taken total number of electrons, either be it's like you can think of it as total number of electrons present in the lone pair.
So is it minus 1?
You're not considering the charge, you're just considering number of electrons. Actually, you're talking about overall formal charge. Yeah. Minus में आ सकता है definitely. So you have minus 4 minus 2 minus half of, you have 1, 2, 3, 4, 5, 6 pairs of electrons being shared. That's 4 minus 2 minus 3, that is equal to minus 1. So the formal charge on minus 1 is carbon, which means that if you compare carbon with carbon in carbon monoxide, it has netted 1 electron. Similarly, if you calculate the formal charge on oxygen, oxygen by default has 6 electrons, minus lone pair is just 2, minus shared pair is 1, 2, 3, 4, 5, 6. So half of 6, that is equal to 6 minus 2 minus 3. It's basically plus 1. Okay. So oxygen has net result, like by forming this compound with carbon, it has given up on 1 electron and carbon has net gained 1 electron. So this will help you figure out, okay, formal charge on carbon is -1, formal charge on oxygen is +1. You can figure out what how the electrons are distributed, shared between both the atoms. Second thing is you can also figure out based on that, is it going to be stable, is it going to be unstable, or how it basically will react, like how it will undergo reactions, you know, in different situations. You can kind of figure that out. Yeah. You guys understand the formal charge calculation? So it's total number.
Yes, ma'am.
So basically,
Between formal charge and oxidation state, I didn't understand.
no, formal charge, this is the calculation. Oxidation state is different from formal charge. That's why I said you can think of it as a precursor to formal charge. Your understanding of it can, you know, kind of similar things they're talking about, but obviously there are different things. That's why you can't use the terms interchangeably. In case of oxidation state, it relates more to the electronegativities. So oxygen is more electronegative, so it is going to try and pull the electrons towards itself, which means that, you know, like, okay, so then how is the charge kind of distributed? So that's what we'll be talking about in oxidation state. Formal charge is purely based on the number of electrons compared to when the atom was in a neutral state versus when it is in a compound wala state, like what's happening in that case.
Ma'am, I have a small doubt. How does carbon has 2 lone pairs? I thought it only has 1.
It has 1 lone pair, but एक pair में 2 electrons है. So that's what I was saying. Think of it as, instead of writing number of lone pair, let me write it as total number of electrons in lone pair. Think of it that way. And total number of electrons that are shared. Total number of,
Ma'am,
yeah.
so like if we're calculating formal charge, then the lone pairs will only be like the lone pairs on the atom in question, right?
Correct. Yes. That is why we specifically say formal charge on carbon. Then you look at the lone pairs on carbon. When you're considering formal charge on oxygen, then it's, you look at the lone pairs in oxygen. So this is the formal charge calculation. Let me see if we can do a couple more questions on this. Then we'll go to the next part. Okay, so the structure of carbonate ion. Do you guys want to try carbonate ion ka structure? Figure out. First,
Okay, ma'am.
yeah. Do you remember what is the formula for carbonate ion?
CO3?
CO3 ion hai. So along with that, what do you have?
HCO3.
No, that's bicarbonate. So carbonate is purely CO3, yes. Valency kya hoga? When I say ion, it should have charge, right? Kitna charge hai ispe?
-2.
Correct. CO3 2 minus is carbonate. So try and figure out the structure. I'll give it to you guys in a couple of minutes, but you guys just give it a try. So once you figure out the structure, calculate the formal charge on carbon. You guys get it? क्या हो रहा है? So, which one would be the central atom?
Carbon.
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 You have 3 oxygens. So let's put it here. Then what happens? How do you distribute the electrons?
It can have 3 single bonds with each of the oxygen, and then 1 double bond with one of them.
Okay. Then are you able to distribute rest of the electrons? Then based on that, we need to figure out if carbon would have an expanded octet or how to proceed.
Ma'am, I didn't understand the meaning of expanded octet.
So technically, these p block elements can have 8 electrons in the outermost shell, right? So, but some elements, if they have more than 8 electrons in the outermost shell, that's what expanded octet is. Like in the case of sulfur, yeah, there's 12 electrons. That's more than 8. So your octet has been expanded. So more than 8 expanded octet. So uska counterpart, like where there's deficiency of electrons, so that's called incomplete octet. In this case, the exact octet aa gaya, I guess. Check if the electrons are being distributed evenly.
22 total, and then 2 minus, so 24 total.
20 is, yeah, so you have 3, right? 16
Yeah.
18 plus, plus 2 from this thing. So that's 24 electrons. No, 26 electrons. 20 plus 6. So out of which 1, 2, 3, 4, 5, 6, 7, 8 we have already distributed.
It's 24, right?
It will be 24, right? Not 26, yeah.
4 plus 18 plus 2.
Sorry, 4, 6, 9. My bad. Correct. 24 is right. Okay. So 24 में से 8 we have distributed, 16 among these oxygens. So let's start with the double bonded one. So 2 of them, 3, 4, 5, 6. So इसका octet complete हो गया. 8 plus 6, 14. So 10 more electrons.
The oxygen will have 10, right?
Why?
Oh, sorry, 8. Yeah, sorry.
So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. 24 electrons distributed there. So this is the structure for carbonate ion. Okay.
Ma'am, the double bond can be with any oxygen atom, right?
Yeah, can be with any oxygen. In fact, it will be distributed. It is usually rotating amongst, the double bond keeps rotating amongst the different oxygens. We'll talk about that concept later. But yeah. Look, all of this is in 3D space. If I just like turn this around this way, it's going to come with this oxygen. So doesn't matter. Yeah, but technically, yeah, this is the structure for carbonate ion. एक oxygen के साथ double bond, the other two are going to have single bonds with extra electrons. Okay. So now,
Could you say the formula for formal charge again? I forgot to note it down.
So you note it down, no? Like start taking notes from this onwards. We'll be talking about serious stuff.
Is the charge -4?
On carbon?
Yeah.
No, shouldn't be. See, its total free atom में कितना है? Minus the total number of electrons in the lone pair, because again that belongs to like unka status change nahi hua. Minus half of the number of electrons that are shared. Okay, because they are shared, you only get half of the charge belonging to those. So total valence electrons, carbon में there's 4 minus.
Ma'am, is it +2?
+2 आया क्या? Are there any lone pair of electrons on carbon?
No.
0 minus half of कितने bond pairs है total carbon में?
8.
8.
Oh, sorry, I forgot to half it. I did 4 minus 8, so I got -4.
8 is correct. You need to consider the total number of electrons in this case. So it's going to be 4 minus 4, that is 0. So formal charge is 0. Everything is like, carbon neither lost nor gained any electron, sharing it even. What about the guys, Arnav, Adat, you guys getting it? Calculating? Kya ho raha hai?
Still calculating, 1 minute.
Ma'am, how did we get 8? I did not understand.
This is total number of electrons that are shared, no? So how many electrons are being shared with carbon? Like how many electrons are there around carbon, which it is sharing with another atom? Think of it that way. So all the electrons that are present around carbon are bonded pairs. So all the 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8 electrons are present in the shared pair of electrons. So that is why it is half of 8.
Yes, ma'am.
Yeah. So even this lone pair, don't consider pair, consider the total number of electrons that are there in the lone pair of electrons. That are there as lone pairs. So think of it that way. So all the numbers here never go with pairs of electrons. All of this is supposed to be the total number of electrons only. No confusion. We need to get the number of electrons. Yeah, got it? Done?
Yes, ma'am.
Okay. Then we have points like limitations of octet rule. Two of those we've already come across. I'll quickly discuss the others also. So limitations, you can note this down. You may get questions based on this, like MCQ assertion based on that. Limitations of octet. So octet rule as presented by Lewis is the one who presented it. Okay. So one is the incomplete octet. Incomplete octet. So this you will come across, like in case there's an electron deficient atom in the center. So a couple of examples I already discussed, like you have BeCl2, BF3, even AlCl3. Like I know you may think of AlCl3 as ionic compound, but it has covalent properties also. In fact, it behaves a lot like covalent compounds, and it forms. Yeah, it forms like coordinate complexes and all that. So Lewis, because he was insistent on octet, could not explain the formation of these compounds, like could not explain why there are exceptions to it. Then you have the case of expanded octet, just like we saw. So this you have electron-rich molecules like sulfate ion and all that. So for example, like this usually happens in atoms. Like you will observe this from the 3p period, like sulfur, phosphorus, like wherever you have empty d orbital present, those are the kind of atoms that you will observe expanded octet in. So carbon you don't find expanded octet in carbon because it has only 2 orbitals or usme empty d orbitals nahi hai. But wherever you have empty d orbitals, that's where you find expanded octet. So accordingly, sulfur like SF6, PCl5, sulfate ion, even phosphate ion, all of those show expanded octet, which the octet rule could not explain. Third, yeah.
I have a doubt. So like you said that AlCl3 also shows covalent properties, right? So is there like a type of name or something for combinations which show both properties of both types of bonds?
No,
Or is it like some exception?
It's not an exception. Like you find a lot of cases where, like, no, what I'm trying to say is intuitively you may think of AlCl3 as ionic because aluminium is a metal, chlorine is a non-metal, but in fact it tends towards the covalent side of things. That's what I meant. So if I in reactions and all that, so there are some organic reactions where AlCl3 is taken as a reagent. So it's not exactly a catalyst. It is essential for the reaction to happen, but it itself is not involved in the main reactant or product. So it gets regenerated by the end of it. So there you can, it is like clearly visible that AlCl3 is taking part as a covalent compound, the way it behaves. Like that. Okay. So then there are some odd number, you have something called odd electron molecules. So like molecules that have odd number of electrons, which octet rule could not explain. Like you can't figure out how the electron pairs are shared or like what's going on there. So examples being NO and NO2 plus, these species. So Lewis could not explain like how are these species being formed. The hint is that like basically they exist like depending on temperature and pressure conditions, they may also exist as dimers, like two NO molecules will get together and form like the octet thing. But knowing what they knew at that point of time, like Lewis could not explain, okay, what is the structure of NO? Like how is it forming a stable structure on its own? Because there's odd number of electrons. You could not distribute it in pairs of electrons. And then you have, he could not explain how so there's octet based on chemical inertness. Like his octet, he figured it out like because inert gases have octet configuration, then inert gases are not reacting. So, like octet configuration was something that atoms aspired for, like they wanted to have that noble gas configuration. So when like the octet rule is based on like it is directly related to the chemical inertness. So could not explain why some inert gases were forming compounds. Yeah, so inert gases, especially xenon, forms a lot of compounds. So you have XeF2, XeO2, then krypton, KrF2. So there are some inert gases that form chemical compounds, which is very, very counterintuitive at this point of time. But yeah, they do exist, and Lewis rule could not explain, what's going on there. Like why are inert gases forming compounds? The actual fact is because again, like molecules are surrounded by electrons, right? And they have their own special properties. Here you've studied about electronegativity and electron affinity and all of that. So oxygen and fluorine are extremely electronegative, that they are capable of attracting the electrons from inert gases also. And that is the reason you will find inert gases forming compounds only with fluorine and oxygen in the case of xenon. And krypton doesn't react with oxygen also. It is capable of reacting only with fluorine. So these reactions are also like not spontaneous, like they don't happen naturally, like they don't react in air as they are. If you initiate the reaction, then it's going to happen, like under specific conditions. But doesn't dispute the fact that these compounds do exist, and Lewis could not explain the structures of these compounds. Okay.
What is it written? Like I could not read that. Chemical based, octet based chemical.
Inertness. INERTNESS, inertness. So Lewis said that once you have octet configuration, you're going to be inert. Like you won't take part in reactions, because the whole purpose of forming molecules is to get that octet configuration. So if that is the case, he could not explain why noble gases that have octet configuration are still able to form these compounds. That's the point. And apart from this, the fifth point is he's just giving you information of how the electrons are shared. He's not talking about, he's not giving any physical quantities like bond energies and all these bond parameters. He's not giving you the bond structures. He's not giving you the shape of the molecule. Like we don't have any other information except how the electrons are distributed between the atoms. That's another limitation of the octet rule. Yeah. But it was like the very first attempt. You can think of it as Rutherford's counterpart. Rutherford was the first one to tell that there is a nucleus and electron revolving around it, but he could not give at what distance, how many electrons, how are they revolving and all of that. Similarly, in the case of Lewis, he's the first one to talk about the driving force behind why chemical like atoms form molecules. And he also could give, based on that logic, what the structure of certain species are, but that's about it. Like he could not give you the shape of the molecule. He could not give, further energies and bond lengths and, physical quantities related to these chemical bonds. ठीक है? Okay, let me know when you guys are ready to go to the next part. Also, I would like you guys to keep your videos on because you're being like really quiet.
Ma'am, can you? Yeah, okay.
Yeah, please keep your videos on because you're also being quiet, and I don't know if you are following or not following or like bored or what's happening.
Ma'am, the last, what's the last molecule?
Oh, this is KRF2.
What's Kr? Krypton, right?
Yeah, Kr is krypton. Krypton difluoride. Also, yeah, this chapter, like the beginning part of it is going to be a lot of theory, but this is like really important theory. Lewis structure, not so much, but whatever we'll be talking about from now onwards is going to be a really important theory because we are going to use these words in all of the chapters henceforth. Especially the bond parameters part is like extremely important. We'll be coming back to dipole moments. We'll be coming back to partial charges. We'll be coming back to, bond energies, bond length, all of that. Organic chemistry may the whole part about dipole moments and how electrons are distributed is really important. Thermodynamics may will be coming back to the bond energies. So yeah, like it's going to be very theory heavy, but it's important theory. Like these are the things you guys need to know.
Does this chapter have like any numericals?
No numericals. So maximum logic based, we have already completed it. It was VSEPR, it was hybridization. And then molecular orbital theory is going to be similar to electronic configuration that we did in atomic structure. That's it. Dipole moment, yeah, thoda sa numerical ho sakta hai, but that's not like, again, it's not, no, it's not numerical. That's also mostly understanding and logic based, but not numbers based. Okay.
But how do you calculate like dipole moment? Is there like a formula and stuff? Do we have it this year?
No, you don't have it this year. You don't have the formula for dipole moment. That gets a little too complicated. So you have to get into, you need to figure out how the charges are aligned, and it gets a little complicated. You don't have that this year. Okay. All right. Ionic bond. So we'll start off, we'll talk about ionic bond and then get on to covalent bond. Okay. Ionic bond, you know what it is? It's a bond formed between ions. And the force that's keeping ionic bonds together is, what type of force is it? So it's formed by between a positively charged ion and negatively charged ion, held by what type of forces? Yes, hello.
Intermolecular attractive forces.
पॉजिटिव चार्ज नेगेटिव चार्ज के बीच में कौन से फोर्सेस होते हैं?
Attractive forces.
Gravitational force is also an attractive force. Do you find gravitational force between two ions?
See, I know what we're talking about. I can't like place my tongue on it.
Electron attraction force, something.
Close. Other, yeah, you have the. You have.
Because we had two only, if I remember.
Hmm.
Oh, is it electrostatic force?
Correct. Electrostatic force.
So told us to put it down. That's why.
That's electrostatic forces of attraction. Attraction because positive charge and negative charge. Agar repulsion hota hai, to yeah, you don't have an ionic bond. They both will like eat each other out. Okay, so it's electrostatic forces of attraction between positively charged ion and negatively charged ion. So you have an ionic bond there. So formation, you guys have done this in grade 10. How is an ionic bond formed? So you have a cation losing an electron, or an atom losing an electropositive atom losing electrons, forming a cation. What would be the energy change in this particular phenomenon? So what energy is involved in this particular reaction? Like if there is energy.
Ionization energy.
Very good. So the energy change associated with this is ionization enthalpy. Use words like enthalpy now, like you need to get a little more comfortable with it. So this is ionization enthalpy. Then इससे positively charged ion आ गया. Negatively charged ion, let's call another thing, X, gains electron, forms a negatively charged ion. So what is the energy change associated with this?
Electron gain enthalpy.
Electron gain enthalpy, yes. Okay. So you have a positively charged, negatively charged. They both attract each other. So M plus X minus will attract each other and form your ionic compound MX. Okay. If we had to get like literal about it, so neutral gaseous atom say ion is formed. Here also you take a neutral gaseous ion. So this gaseous ion will bond with each other, finally forming an ionic solid. Okay, so this is the formation of ionic compound. So in order for ionic bonds or ionic compounds to form, what is ideal? Like what kind of values should I and delta electron gain enthalpy, no? Let's call it delta H is enthalpy, Eg represents electron gain. So what should be the values of IE and delta H so that an ionic compound can form easily?
Ma'am, could you repeat your question?
Yeah. So what should the values of IE and delta H be so that an ionic compound or an ionic bond can form easily? So let's take it one step at a time. Ionization enthalpy should be like, what sort of value should it be? One, should it be a positive value or a negative value? And second, should it be like a high value or a low value?
A low value.
Correct. So if you have a low ionization enthalpy, this is going to be pretty easy because ionization enthalpy is the energy required for this process to happen, right? So if the energy required is low enough, then atom can easily form an ion, which means that one half of your ionic bond is easily covered. Now, second point, what sort of values do you want delta H to have so that this process gets easier?
Low.
A negative value.
You should have a negative value, yes. Kaveri, can you explain when you said low? Like, should the electron gain enthalpy be a small amount, or like how exactly did you mean that?
I mean, I don't know if it releases less amount of energy in order to gain an electron, then it will be an easier process.
No. Think about it a little more. Okay. So I've been saying that stability refers, like it relates directly with energy, right? So let's say your energy was E1. After a particular process, it went down to E2 over here. So after another process, it went even lower to E3. Which one is more stable? The one where it went down to E2 or the one where it went down to E3? Let's call it before and after. So process 2 के बाद it went down to E2. Process 3 के बाद it went down to E3. So which of the two cases would be more stable between these two? Let's call this state A and let's call this state B. So which is more stable, A or B?
If high stability means low energy, so E3 has a lower energy, which means that it will be more stable.
Correct, right? So if you look at the difference in energy, which one has a greater difference in energy, like process A or process B?
B.
Process B, right? So which means that if you look at final energy minus initial energy, which one will have a higher value of the difference?
E3 minus E1.
E3 minus E1, right? So that way, if you apply it to your electron gain enthalpy, so your delta H should have, like, what kind of value should it have? High negative value or a low negative value?
Low energy, so it would be a higher negative value.
Correct. Yeah. So your electron gain enthalpy, you should have high negative value. Ionization energy, you should have low value. So you can figure out which one is likely to form an ionic bond just by looking at the ionization enthalpies and electron gain enthalpies. So another version of electron gain enthalpy is called electron affinity. So electron affinity is like it's same as electron gain enthalpy, just the sign is reversed. Okay, so you can think of low ionization enthalpy and high electron affinity, or a high negative electron affinity, electron gain enthalpy will favor ionic bonds to form.
I had a doubt. I could not understand that part. So, for example, for electron gain enthalpy, if it is more negative for ionic bonds, that for anything rather, it is more stable because it's obtaining the octet state, right? Or something like that.
Correct. Yeah.
Okay.
Okay. So both of these are obtaining octet state. So whenever you have ions being formed, it's only because they're obtaining octet state. So whenever you come across something that's not octet, whenever you come across, electron deficiency or expanded octet, more often than not, it's going to be covalent compound or coordinate bond. So you're not going to come across that in ionic bond. Ionic may, like, whenever there's ions being formed, except for D block and F block elements, like wahan pe you won't have octet because you have the D electrons and the F electrons and all of that involved. But S and P electrons, usually it's, you always get octet configuration. Usually we nahi. S and P, almost like 70-80% of the cases you get octet configuration. Yeah. So favorable for ionic bonds to form, low values of ionization enthalpy and high negative values of electron gain enthalpy. Okay. Suppose I come across, like, let's look at this for the formation of what do you call? So sodium chloride.
Ma'am, could you just show the previous slides for 1 minute? Okay, ma'am, done.
Okay. All right. Let's look at the formation of sodium chloride. So can you guys Google and look up the values for sodium chloride? So sodium chloride first formula क्या है?
NaCl.
NaCl. उसमें which is the cation, which is the anion?
Na is the cation.
Cation is Na and anion Cl.
Anion, correct. Which means that Na is the one that's going to form Na plus. Can you guys let me know what is the ionization enthalpy for this? Just do a quick Google on your phones or on your computers and let me know. Similarly, find out and let me know what is the electron gain enthalpy for chlorine, Cl minus formation.
180 Kelvin.
180 Kelvin. Kelvin किसका यूनिट है?
Kelvin is temperature.
Ionization enthalpy is a kind of energy, तो इसका units क्या होना चाहिए?
What is cal per mole?
Oh, that's calories per mole. Can you, like, is it possible?
1 Kelvin calories per mole.
180 Kelvin nahi hai. Acha. So you must be seeing the value 180 kcal per mole, right? So this stands for kilocalories. Kelvin hamesha you will find it as a capital K. Capital K hai, so that is Kelvin. So if it is a small K, that's kilocalories per mole. Okay. Just because we have a habit of using SI units, can you find the value in joules? Mostly you will find it in joules per mole. Can you check that? So capital K is Kelvin. If it is a small k, that it's basically kilo. Just like kilo. Huh.
753.1
495.8.
No, दो अलग-अलग values आए. Kaveri, what value were you talking about?
180 kilocal per mole is equal to 753.12 kilojoules per mole.
Kilojoules. Okay, Smera, what value did you get?
I'm getting 495.8 kilojoules per mole.
That's so strange. एक ही सोडियम के लिए दो अलग-अलग values क्यों होते हैं? ये कैसे हो सकता है? Can anybody else check?
It says 4 kilojoules per mole.
क्या? How?
The enthalpy of solution of sodium chloride.
Sodium chloride? No, we are talking about ionization enthalpy of sodium alone. So only for this particular process.
Yeah, even I'm getting 495.8.
Oh, I did for any
496. 496 to kj mole. That's round off.
Cool. Okay, so this is positive 496 kilojoules per mole. Okay. Cl minus के लिए, like to form chloride ion, what is the electron gain enthalpy?
Minus 348 kilojoules per mole.
Okay. Minus 348 kilojoules per mole. Okay. So if you add them up, usually you get Na plus Cl gives electron cancel ho gaya. Na plus and Cl minus, so NaCl, right? So similarly, if I add up the energies, like Na plus form karne ke liye, I'll need 496. Cl minus form karne ke liye, I'm getting 348 minus 348. So overall net delta H kitna aa raha hai? 496 minus 348.
148.
148 kilojoules per mole. Now, in this case, I'm getting a positive value. So delta H positive matlab. So delta H usually represents, delta anything represents the final minus initial, right? So if my final minus initial, I'm getting a positive value, does it mean that I'm losing energy, or am I like, what is the net result? Is it a lower value of
You
energy?
will gain energy.
It's a higher value of energy. Matlab, some external source is required to put extra energy for this process to happen, right? But it's not difficult to form NaCl. So NaCl, like if you put sodium, if you put chlorine in a box and then you shake them up, it is going to form NaCl and it's going to be explosive. So that doesn't exactly relate with our mathematical calculations. So how is that possible? What do you guys think? Is that calculation wrong, or is there something missing? Like, what are we missing? Like, do you guys understand what is the conflict here? Like, why what is the doubt here? What is the issue here?
Yeah, like when we're making these two elements react, they can like easily form it without the help of more extra energy. But according to our calculations, we need more energy for the reaction to happen.
Correct. So the reason why ionic bonds are able to form, so the key is in the states that we are taking. So ionic compounds, what is the usual physical state of ionic compounds?
Solids.
They're usually solids, right? So when you have Na plus ion in gaseous state and Cl minus ion in gaseous state, in gaseous state, they're not going to form NaCl. So the Na plus gaseous state plus Cl minus gaseous state, they have to come together and form NaCl solid. Okay. Now, what is the defining difference between gaseous state and solid state? Like, what do you know about gaseous state and solid state? Main difference. Where is
In
that?
gaseous state, they're like loosely arranged.
Yes.
Intermolecular forces of attraction are very high in solids and very low in gases.
That's again a property of solids and gases. But what defines solids and gases is how the atoms are or particles are arranged. Okay, so go by that. So in gaseous state, as Sanat said, they are all spread out everywhere. How are the particles arranged in solid state?
Very rigidly.
Very rigidly, like they're all near each other,
Just
right?
bunched up together.
Correct. So the way, like if you zoom in and actually try to visualize the atoms, this is what NaCl looks like. So I have animated models here, like illustrations here. But any ionic compound, you're going to find it in this kind of a arrangement. So you don't have individual molecules of Na and Cl, like NaCl. That does not mean anything when it comes to ionic compounds because it's all charges. So every positive charge is going to attract negative charge around it. Every negative charge is going to attract like positive charge around it. Okay. So this is what salt structure looks like if you were to look at, the individual pieces of how the ions are arranged. So this sort of structure, it has a name. So this is called a lattice structure. Okay, so it's called lattice structure. And there is, the process of the gases coming together and forming, like the electrostatic forces of attraction, forming bonds between these particles. So there is an energy change associated with it, and that particular energy is called lattice energy. Okay, so you can literally think of it as lattice energy is the energy that's holding together the whole crystal structure, the whole ionic solid together. So without the lattice energy, all of these, each of these particles is going to, float around in a gaseous state. So they're coming together because of electrostatic forces of attraction. So what is the energy associated with that if you consider? So that's nothing but lattice energy.
So is the external energy that we need to provide, is that the same as lattice energy?
Not exactly the same. So lattice energy is its own energy. And if the lattice energy is sufficient to overcome that difference in energy that we saw, then the ionic compound is going to happily form without any, external help as such. So lattice energy is its own energy. So this lattice energy is calculated experimentally, and for NaCl, it happened to be, I can Google it and show you. So
But what does it depend on, lattice energy?
It depends on the interaction. So it depends on the size of the molecules. Like we'll come across that. We'll discuss that in a bit. Okay. So you can see here. So experimental, like lattice energy can only be calculated experimentally, and it was found that NaCl के लिए the lattice energy is minus 786 kilojoules per mole. So when you take into consideration, when you add up the ionization enthalpy, the electron gain enthalpy, and also the lattice energy, we can see that the overall value is negative, which means that NaCl is more stable as NaCl ionic solid rather than Na plus Cl minus, or as individual Na atoms and Cl atoms. So that is the reason NaCl can naturally form, like it can easily form. So that particular formation is perfectly feasible.
Ma'am, I
Yeah.
have a doubt.
Hmm.
So will the lattice energy always be like extra?
Lattice energy extra in the sense?
Like here like before we needed extra energy, right? If we didn't have the lattice energy, we needed extra energy for the molecule to form.
Yeah.
So, but after we got the lattice energy, we had like it was able to form properly.
Correct.
So, is there any instance when lattice energy is like insufficient?
I can't think anything off the top of my head, but there may be. Like I'll have to do a search and then check it. We can look at that. But
Ma'am,
yeah.
if lattice energy is the energy that is being given to the like suppose NaCl, like where like it's being provided externally, right? So why is this?
No. That's where you're wrong. So lattice energy is its own thing. Lattice energy is the energy that is released when Na plus and Cl minus, all the ions are coming together and forming that solid structure. So that's what I said. Yeah. Lattice energy is its own thing, and it is released when these ionic bonds are being formed. It is automatic. It is inherent in nature. So that explains why NaCl is being formed, independently as a compound, and you don't need any external source for it to form, because the lattice energy of NaCl is high enough that it overcomes any other energy that is required for ionization or anything else. So that's kind of what it means. Okay. So I'll give you guys, we'll discuss the definition of lattice energy now. So we'll come back to this. So even though, like just ionization and electron gain enthalpies are not sufficient, you also need that solid structure to form stably. And that stability is, you can calculate it in the form of lattice energy. So the definition of lattice energy, you can say, or call it lattice enthalpy. So lattice enthalpy is the energy required to completely separate one mole of, that's why all your values are in kilojoules per mole, because your calculation, you're standardizing for 1 mole for easy comparison. So separate 1 mole of solid ionic compound into gaseous constituent ions. Okay, so you can see that we said, what is lattice enthalpy? It is the energy required to completely separate the solid into gaseous ions. which means that if you're having to apply energy to break that crystal structure apart, it means that the crystal structure itself is being naturally held with so much force. Like those bonds have enough energy that you're trying to put in extra energy to break them. So if you look at the reverse process, so instead of separating 1 mole of ionic compounds, if you're looking at it from the other side, if you have gaseous constituent ions that you're putting together, so instead of separating, you're putting them together. If you have to provide energy to separate it, uska reverse process, your energy is going to be released. Yeah.
You said that lattice enthalpy is like when they come together, they in solid form, that's when they release the energy, right? So I don't understand how gaseous thing came into this.
No, because your natural ions are in gaseous state. So if you look at these, we have your ionization enthalpy and electron gain enthalpy are meant for, like you're taking a neutral gaseous atom and then removing an electron. So what you get is a cation in gaseous state. Similarly, you're taking a neutral gaseous atom, adding an electron. So what you essentially get is an anion in the gaseous state. So you have cations in the gaseous state, anions in the gaseous state. When you're putting them together and you're getting a solid ionic compound, so the delta H in this process refers to the lattice enthalpy. Okay, make sense, Kaveri?
I still didn't understand that. Like gaseous and gaseous combine to form solid.
Okay, visualize it this way. So let's say the red is Na plus, Na, and Na has an electron. You have blue is Cl. Cl has 7 electrons. So Na is gaining 1 electron to form cation, right? Sorry, Na is not gaining. So Na is losing an electron to form cation. Na gives Na plus. So एक electron जो था, that's lost. And similarly, Cl is the one that gains an electron to form Cl minus. It has 8 electrons. Okay. Now, when you're looking at ionization and electron gain, all of this is applicable for gaseous atoms and gaseous ions. Do you remember the definition of ionization enthalpy and electron gain enthalpy?
Yeah, for an isolated neutral gaseous atom.
Gaseous atom, right? So these processes are happening when atoms and ions are in the gaseous state. So now you have a whole bunch of, like I release some chlorine gas, chlorine ionized ho gaya. So you have gaseous chlorine atoms. Gas matlab they're all like floating here and there. And then you have gaseous sodium atoms, all of them floating around here and there. So isme I have, in this box, I have Na plus and Cl minus, both of them in the gas phase. But when the positive and negative are attracting each other, when you have bonds forming, like the Cl atom has negative charge, it'll attract all the sodium atoms around it. This sodium atom has positive charge, it's going to attract all the chlorine atoms around it. So when they all are attracting each other, your final product is going to look like this. So I have a Cl minus atom it's going to attract all the sodium atoms, form an ionic bond, and they're all going to be around each other, like in the 3D space. It's going to be a cube, but here I'll just show it to you as a square. Similarly, a red color sodium atom, this atom that's there, the positive charge is going to attract the negative charge. So this is going to be surrounded by all the chlorine atoms. So that's going to go on. Again, chlorine atom has negative charge. It's going to be surrounded by all the positive sodium atoms. Even this chlorine ion, even this chloride ion. Again, these sodium atoms are going to attract all the, negatively charged chloride atom, like ions around them. Yeah. So this way, because of the attractive forces, it's going to form like a large crystalline structure. Now, when all these particles are arranged so close to each other, what do you think will be the physical state of this compound?
Solid.
This is going to be solid. So this is NaCl solid. Okay. So the energy that is involved in this process. So when you're going from gaseous to solid, energy is released. And when you're trying to do the reverse process, when you're trying to separate these out and convert them into gaseous ions, the constituent ions, you need to put in energy. Reverse process के लिए. So that quantity of energy that is required to do this process is lattice enthalpy. So that is what it is.
Okay.
Yeah. Cool. So higher the lattice enthalpy, stable is the structure going to be. And if it is high enough to compensate for the ionization energy and the electron gain enthalpy, you can be sure that the lattice, the ionic bond is going to be formed. Yeah. So when you look at for ionic bonds to form, favorable conditions are low ionization enthalpies, high negative value of electron gain enthalpies, and the third factor is high negative lattice enthalpies. Or generally like high lattice enthalpy. Okay. So these are
So ma'am, the lattice enthalpy is the energy when we convert it from solid to gas?
so like again, you don't just say it is the enthalpy when we do it. So it is the energy required to separate it from a solid, like separate a solid ionic compound into gaseous ions. If you're defining it, in the other way around, if you're talking about gaseous ionic ions combining to form a solid ionic structure, then you say the energy released when 1 mole of gaseous constituent ions are combining together to form a solid ionic compound. So you need to be very specific. It's not just the energy. It is either it's the energy required or it's the energy released, depending upon what process you're looking at. From what point of view you're looking at. From this point of view or this point of view. Okay? And somebody asked like what it depends on, right? So it depends on two things. One is the charge on the ions. And the second thing is the size of the ions. Okay. So how do you think lattice enthalpy will change based on these two factors? So if charge on the ions is greater, do you think lattice energy will be greater or lesser?
Greater.
Okay, Kaveri is saying greater. Rest of you, what do you say? Do you agree or disagree with her?
I didn't get the question. Could you repeat it again?
So lattice enthalpy depends on these two factors. It depends on the charge that is present on the ions, like between the cation and anion inka charges, and it depends on the size of the ions. So my question is, how does it depend on the charge on the ions? So if the charge on ion is greater, then lattice energy will be greater or lesser? Think about it. So lattice energy, it is coming together as a lattice, as a solid, right? And what is the force that is bringing the ions together? Or what is the force that is holding the cations and anions together?
Electrostatic.
Electrostatic forces, right? Abhi, lattice energy, you can directly think of it as the energy form of the forces that is holding it together. Now, greater is the force, greater is the energy that is required to separate both of them, right? If they're being held really tightly, electrostatic forces of attraction are really strong. It's going to be difficult to separate them. You need to you need to give a lot of energy to separate them. Now, if the charge on the ions is greater, like if you had +2, +3 charges on cation and anion, then would you require more energy to separate them or less energy to separate them? How does the charge affect this thing?
If it is more like +2 and +3, the size of the atoms becomes smaller.
We're
So
not
I think
talking
it will.
about size, Rishit. Right now we're
No,
focusing
I'm just
charge.
connecting it like that. So the size becomes smaller, so it's harder to bring out. So I guess when it's positive, we require as much more the number of electron is given away, it is harder to separate an electron. So
Absolutely. That is correct. So Kaveri was right earlier. So greater is the charge on ions. And Rishit, this again, charge, like yes, it affects size, but you can still have small ions with greater charge, like nitride ion, N3 minus. N is a small ion, 3 minus charge is greater charge, right? So don't connect it with size as such, but yes, greater is the charge, greater is the lattice enthalpy. It's going to be directly proportional. Okay, because the energy that is applied, like again, energy directly related to forces of attraction. Now, just like how gravitational force is related to masses. So masses zyada hai, so gravitational force is also a lot, right? Similarly, electrostatic forces of attraction are also directly related to the charge. So if the amount of charge is more, then the electrostatic forces of attraction is also more. So more force, more attraction means harder to separate, you need to give more energy. Now going by the logic, how do you think the size of ions will affect the lattice energy? Smira, what do you think?
It will be indirectly proportional.
Can you repeat that, Smira? Voice was a little low.
Miss, can you hear me now?
Better.
Yes. So size would be indirectly proportional.
Inversely proportional. Correct. So अगर size ज़्यादा है, then the two ions will be far away if one is like really large, one is small, or if both the atoms are large, like as the size increases, the distance between each ion also increases, the space between them increases. So if the distance increases, the quantity of force decreases. So it'll be easier to separate them out. So lattice enthalpy, high charge, small size will have like extremely high lattice enthalpy. But as the size of ions increases, the lattice enthalpy is going to decrease. So you can see that in action, like I was looking for NaCl lattice enthalpy, right? So you can see that in like trend over here. So here they're comparing NaCl, NaBr, NaI. So cation का size constant है, but anion का size increase हो रहा है. So you can see that, and charge is also the same. It's all +1, -1 in all the cases, right? And you can see that the lattice enthalpy is decreasing as the size increases. NaCl के लिए smallest ions you have -786. When it comes to iodide, it has reduced to -704. And then
Ma'am,
yeah.
like the compounds are different, but it says the structure type is the same.
Oh, don't worry about it now. Like solid state, you have structure type. Structure is basically how are the ions arranged? Like, are they arranged exactly in a cubical state, or are they arranged like, एक row ऐसा है, दूसरा row in between the gaps, like are they arranged here? So there are certain structures called face-centered cube, hexagonal close pack, like all of that. So don't worry about that right now. So this is literally, how are the individual atoms arranged? So NaCl, NaBr, NaI all have the same structure type, same as NaCl. ये जो भी structure ले रहा है, same structure. CSCl is a completely different this thing. That's what it represents. But yeah, and then compare it with CSCl. Now, if you compare sodium and cesium, which cesium is a much bigger ion compared to sodium. Sodium upar beta hai, cesium is right at the end. So you can see that the lattice enthalpy was also decreased based on that. 786 से 657 हो गया. Okay. So that's kind of how you compare, like how you can roughly get the idea of lattice enthalpies based on the charge and the structure. So that's what lattice enthalpy depends on, the charge between the ions and the size of the ions. Directly proportional to the charge and inversely proportional to the size. Okay, so this is all about lattice enthalpy, and this is all about ionic compounds. Actually, there's one more bit. So you have Fahan's rules on ionic compounds. Okay, Fahan's rules. Okay, this we will talk about after talking about dipole moment. Okay. इसके बाद we have stuff about bond parameters. Bond parameters. So bond parameters is just different aspects, like parameters related to any chemical bond. Okay, so you have like your obvious ones. The first one is bond length. How do you define bond length?
The distance between like the nucleus of two atoms.
Absolutely. So it's the distance between the nucleus. If you were to be specific, this two atoms that are chemically bonded to each other. Okay, not two random atoms. So it's the internuclear distance, the distance between the nuclei of two bonded atoms. If you had to be technical about it, call it the equilibrium distance. So why do we use the term equilibrium? Is atoms are always moving, right? Like they have vibrational motion, they have rotational motion, and they have translational motion. Now, when a bond is formed, like wherever they have formed a bond and then settled down, you know, like if in case they are vibrating against each other, the distance is going to vary. Okay, like in reality, they're not going to vibrate so much, but just to show you, like even if they're vibrating, there's going to be a slight variation in the distance. So you see where they have settled, like you measure the mean distance between both the nuclei, the equilibrium distance between the nuclei of two bonded atoms. Okay. Bond length, experimentally, you can measure it using X-ray diffraction. These are like experimental method techniques to figure this stuff out. So X-ray diffraction and other spectroscopic methods. So we've seen this when we were looking at measurement of atomic radius also. What else? Yeah, the contribution of covalent bond is the covalent radius. So like if you're taking a specific case, if you're measuring the bond length in a specific case where you have two identical atoms, then you can use that to figure out the covalent radius. Yeah, it's pretty straightforward. That's all there is to it. Next, you have bond angle. This is also fairly self-explanatory. What do you mean by bond angle?
Angle between bonds.
Angle between bonds, absolutely right. Now that you've learned about hybridization and all that, what exactly would you measure when you look at a molecule? So it would be the angle between the orbitals containing the bonding electrons. So the technical definition that's given in your book is defined like this. So containing the bonding electron pairs around the central atom in a molecule. Okay, so basically like carbonate here. So you found that these are all the different bonds. So all of this is formed by the overlap of, let's say the p orbital of oxygen or the sp3 orbital of carbon, right? So you consider, okay, is the sp3 or sp2 and this one's sp2, dono ke beech mein what is the angle? That's the bond angle. So it's the angle between the exact orbitals that contain the bonding electron pairs around the central atom. This also is measured using X-ray diffraction.
Ma'am,
Yeah.
in some cases, it's like equatorial and axial angles are different, right? So in that case, what would be the central angle?
It's the same. Again, central atom here. Whenever you're measuring angles, you need, like this is an angle, right? So you need two arms and one vertex. So bond angle ke case mein, your vertex is the central atom and your arms are the orbitals. Now, the thing that you're saying, equatorial, axial and all, depends on the case that you're taking. So if you're taking these two specific orbitals, bonded orbitals, then in dono ke beech mein ek angle rahega. If you're considering these two orbitals, in dono ke beech mein ek dusra angle rahega. It depends from a case-to-case basis, depending on what angle you're considering. But essentially, angle is bonded pairs ke beech mein jo like bonded pairs are there in orbitals, then it's the angle between those orbitals which contain the bonded electron pair. And it is going to be around the central atom. The central atom is the vertex. Uske around jo bhi orbitals hai, that's what you're going to consider. Equatorial, axial, those are just names given to specific situations. Like equatorial bond length matlab equator ke plane mein jo bhi bonds hai unka length hai. Axial bond length matlab axis mein jo bonds hai unka length hai. That's it. They're just names given to specific cases. And bond angle will help you figure out the shape of the molecule. The bond length, say you can approximate, like you can take specific cases and then figure out the atomic radius. Bond angle, say you basically get the shape of the molecule, like a significance. Then number 3, you have bond enthalpy. So what do you mean by bond enthalpy? Any ideas?
Bond energy.
Yes. Now, what do you mean by bond energy? When you say energy, it's a physical quantity, right? Like, yeah.
Could you give me a hint?
No. What do you mean by bond energy?
The energy required to break the bond.
Absolutely. Okay. So when you talk about enthalpy energy, energy is what? Capacity to do work, right? So what work are you doing in this case? You're breaking the bond. So, sorry. So bond enthalpy is the amount of energy. When it's a physical quantity, it's a numerical value. So it is the amount of energy required to break. And this is like an actual thing. Like you can talk about bond energy randomly, but when you say bond enthalpy, it is applicable, like it is a specific definition defined for 1 mole of the molecules. So it's the amount of energy required to break required to break 1 mole of bonds of a type between 2 atoms. This also you're taking it specifically in the gaseous state. Okay. And bond enthalpy ka unit, just like your other enthalpies, you measure it in kilojoules per mole. Per mole, because you're measuring it, you want to break it for 1 mole of bonds, and it is the amount of energy, so the unit's going to be kilojoules per mole. Okay. So it is going to be specific for a type of bond between 2 atoms. So for example, carbon oxygen ke beech mein, if you're considering, so carbon oxygen ke beech mein, this bond is going to be 1 value. So let's say delta E1. Carbon hydrogen ke beech mein, this is going to change. It's going to be another value, delta E2. And if you consider carbon double bond carbon, this is going to be again a different value. So it is the amount of energy, that's enthalpy part of it, to break 1 mole of bonds So of a type, so single bond or double bond ke beech mein it is going to be different between two atoms. So it is defined for a specific pair of atoms. So carbon, oxygen, carbon, hydrogen, enthalpies are going to be completely different. So even if the type of bond changes, double bond, single bond, triple bond, the energies, the enthalpies calculated are also going to be completely different. Okay. The significance of bond enthalpy. So what can you conclude based on the values of bond enthalpy? Like, for example, if you find that a specific enthalpy happens to be greater. So greater is the bond enthalpy. What does this mean?
The amount of energy required to break a bond is higher.
That is like, that's what is the meaning of greater is the bond enthalpy. You just give the meaning of it. तो उससे क्या conclude कर सकते हैं?
The bond is stronger.
Absolutely.
Like the more energy it takes.
Correct.
Bond is greater.
Yes. So greater is the bond enthalpy. That implies that stronger is the bond. So if you compare two bond enthalpy values, if one is greater than the other, it means that that bond is stronger than the other. So that will not break easily. Yeah. Measurement, when it comes to measuring the bond enthalpies. So in the case of polyatomic molecules, so in the case of polyatomic molecules, it's slightly different, slightly more complicated. You use something called mean bond enthalpy. So mean or average bond enthalpy. Okay, so what it means that, so for example, you want to calculate the bond enthalpy in methane. Methane is CH4, right? So carbon has 4 bonds with hydrogen, tetrahedral shape. Now it is the same atoms, same pair of atoms. It is carbon, hydrogen only. It is the same type of bond also, like all of them are single bonds. But when you're experimentally calculating it, right? So when you're trying to calculate it experimentally, you won't get the same value for all 4 of them. So if you are breaking the bond, amount of energy required to break the bond, right? So if you're breaking the bond, if you're getting CH4, breaking it into CH3 plus H, the amount of energy that you get for this will be different from when you break the second set of bonds. So CH3, if you're breaking it into CH2 plus H. Okay, so the bond enthalpy you get is going to be different. So in this case, you calculate the value for all the 4 cases, and then you take the average of all 4 cases. And that you assign as the bond enthalpy in methane, the bond enthalpy between carbon, hydrogen in methane. Same is the case for water. So water is made of 1 oxygen, 2 hydrogens. When you break this bond and calculate the energy, then after that, if you're breaking this bond and calculating the energy, both of them will not be equal, even though, you know, it's the same pair of atoms and same type of bond. Like the measured experimental value, you're going to get different values. So that is the reason when you're assigning the bond enthalpy of oxygen, hydrogen, and water, you measure these 2 values and then you take the average of both of them. Okay. So it's the measurement of bond enthalpy that's different in these in the case of polyatomic molecules. And because you're taking like average of all the values, you call it mean or mean bond enthalpy or the average bond enthalpy. ठीक है? Clear? Okay. Should we go to the next parameter?
Yes.
Okay. Everyone?
Yes, ma'am.
Yes, ma'am.
Next one is bond order. Rishit is already 5:10. You can have like infinite break after 20 minutes. Okay. All right. What do you mean by bond order? What am I referring to when I say bond order?
Number of bonds.
Absolutely. Bond order refers to the number of bonds between two atoms in a molecule, not between two elements, between two specific atoms. So it's basically, single bond, double bond, triple bond. That's what you call bond order. Adit, do you have a question or something?
No, ma'am.
Yeah. So in the case of single bond, the bond order is 1. In the case of double bond, the bond order is 2. In the case of triple bond, bond order is 3. Another note, isoelectronic molecules will have the identical bond orders. So basically, if you have two molecules and you see that the number of valence electrons along with charge and all, like everything is the same if they are isoelectronic. And then if you count the number of bonds that they have, like all the single bonds, double bonds, triple bonds that they have, you'll find that the total number of bonds they have will be same. Even though the distribution may be different, but as long as the number of electrons are the same, the bond orders are going to be the same. Okay. Yeah. Now that
So, ma'am, for example, it has one bond and then one more double bond. So the double bond and that one bond will be equal to two bonds or three?
3 bonds. So bond order is literally, I mentioned, right? So single bond here, so the bond order is 1. Double bond here, bond order is 2. Triple bond here, the bond order is 3. So in the case of bond order, you're going to consider double bonds like, so if there's a single bond, double bond, you'll consider 1 plus 2 equal to 3. This is applicable in the case of isoelectronic molecules. Say isoelectronic molecules and ions. Because I mentioned, right, species in general, like even if you consider a carbonate ion and another molecule which has the same total number of electrons, then the number of the bond order is going to be. Another little relationship. So as the bond order increases, so greater is the bond order. What can you say about the bond length? So if you compare the bond length of identical atoms, but you have a single bond and a double bond and a triple bond, then which one will be the longest, which one will be the shortest, or do you think they all will be the same?
I think like the double and triple bonds would be shorter than the first one because there's more electrons. So like the forces of attraction would be more, holding them closer.
Correct. So greater is the bond order, lower will be the bond length. So triple bonded atoms, because there's like 3 pairs of electrons, they're going to be closer to each other. Bond length will be smaller. Single bonded, there's only 1 pair, so it's going to be longer. Then what can you say about bond enthalpy? So as the bond order increases, will bond enthalpy be greater or lower?
Greater?
Absolutely right. So even bond enthalpy is going to be greater. Think about it. So if you were to break single bond, you just have to separate out 1 pair of electrons, or separate out, break the bond between 1 pair of electrons. But if you're breaking a double bond, you have to break 2 pairs of electrons. That's going to be more difficult. And if you're breaking a triple bond, you have to do that same thing thrice, because there's 3 pairs of electrons. So as the bond order increases, the bond length decreases, they're closer together, and the bond enthalpy increases. So again, the number of bonds is increasing and they're closer together. It's going to be more difficult to like separate them out. Yeah. So this is all about all the bond parameters. And what about bond angle? So what is the effect of bond order on the bond angle?
Higher the bond order, lower the bond angle.
Why do you think so?
There's more electrons, right? So, wait, no, that's between 2 atoms, not electrons.
Correct. So there's no effect on bond angle. It is like not applicable at all. Yeah, no effect. This bond angle is like between 3 different this thing, right? Bond length is like between both of these. Bond enthalpy also, it deals with only breaking these 2 bonds. Bond, like the angle, see the second and third bond, like knowing what you know now. So these are all going to be pi bonds only, right? Over and above this. So the overall structure is not going to change as such. Doesn't affect the bond angle. Okay. So after this, we've got resonance and bond polarity, like dipole moment. Okay. So we'll do all of that in the next class. Hopefully we'll do this and hybridization behavior. And then we can do molecular orbital theory and hydrogen bonding. We should be able to finish off chemical bonding in the next class.
Ma'am,
Yeah.
so like how much of the chapter is like left? Like is it a lot?
Oh, it's not a lot. So molecular orbital theory, because it's a new theory, just like hybridization and all that, that will take major amount of time. But dipole moment is new, just like how we had bond angle, bond order. Dipole moment is another bond parameter, so that's not going to take a long time. Farn's rules also, there's like 3 specific rules, so that will take 3 rules, another 15 minutes or so. Not a lot. Molecular orbital theory is the only one that's major out of all these. Second major is bond polarity, but that's also fairly easy to understand. It's a small thing. Hydrogen bonding is like really, really easy. Yeah. So next class, I think we'll be able to finish in 2 hours. So remaining time we can spend on questions, the application-based questions. And